So I'm starting. So welcome back, and this session is on chemical and atmospheric sciences, and I am Niloy Ganguly who will be sessioning the chair. And hmm, the first talk is from Dr. Brooks Page on Bayesian inference and meta learning for molecular property predictions with graph neural networks. Dr. Page is an associate professor in machine learning in the Department of Computer Science at University College London. His research focuses on interpretable machine learning, methods for scalable Bayesian inferences, and applications in the sciences. He holds a DPhil, which is like PhD in engineering sciences from University of Oxford, where he was supervised by Frank Wood, a MA in statistics from Columbia University, and a BA in mathematics from Amherst College. So over to you, Dr. Page. The stage is all yours.
Hi, thank you very much for the introduction. Also, thank you for inviting me and having me here. I'm going to present some recent work on molecular property prediction with graph neural networks. Focusing, I'm going to talk a bit about meta learning. I'm going to talk about Bayesian inference in this setting. And I'm also going to give a bit of a background on machine learning for molecules, since I'm the first one in this session. So that should hopefully tee up a bit some of what Miguel, Christophe, and Abir are going to talk about right after me. So hopefully this will also be a good setting and introduction to the session. Let's see, there we go. So as motivation, everything is made out of molecules. So molecules make all the things we know of. They have a huge impact in our lives. And many important challenges can be framed as searching for new molecules or new materials. So this includes drug and medicine design for healthcare. So this is often the one that we sort of jump to as an example, but also it includes things like energy production and storage. So, designing new solar cells or designing new batteries, as well as, slightly more, maybe more ambitious things like greenhouse gas conversion. So, for example, molecules that can break down CO2 into constituent parts. And progress is slow, and it's slow for a few reasons. I think partially this is, molecule and material design requires a lot of human expertise. And it also requires a lot of data, which is very expensive to collect. And it's a high cost of collecting data. It's challenging to make decisions. So it would be really nice to use machine learning to help accelerate this process. And one way in which machine learning can come in is it can help provide alternatives to running computer simulation methods like DFT or molecular dynamics computations, which can take hours or days to compute. Physical experiments can take much longer to run if you have to actually run physical assays. Machine learning methods can make predictions in milliseconds. So if you have an accurate machine learning model, this can be really helpful for doing things like screening large databases of molecules quickly. It's also, I think, really what we'd like to do as well, and Miguel is going to talk about this more, I think, in the next talk, is how we can really incorporate machine learning into the loop, to close the loop. So how can we use the data that we collect to guide synthesis experiments or guide simulations? So, if we're trying to design some new material concept, for example, in this image, a battery, there's a sort of synthesize, test, and then learn from what we just synthesized and tested process. And this is in order to do this well, and in order to close this feedback cycle, a machine learning model that sort of helps us decide what to synthesize and test is going to have to deal with the fact that early on in this process, we might not have very much reliable data because we haven't necessarily synthesized or tested very many things for whatever it is we're trying to measure. And also, we're going to have to deal with the fact that as we explore new things, there's going to be a lot of uncertainty that we'll need to sort of take into account, because we're going to be shifting in distribution from, say, the types of objects, the types of materials we tested early to the types of materials we're testing later on. And so I'll come back to this. But before we look at machine learning of molecules, it's maybe good to think about the settings where we know that machine learning works very, very well. For example, image classification problems. In image classification problems, we really benefit from having at least 3 things that make this something that's really ripe for machine learning to work well in, right? One of it is we have tons of data. We have really web scale data. ImageNet has 14 million images with labels. We also have a clear representation for what these images should how they should be represented, right? They come to us in a matrix or a vector already of different channels with different colors and in a fixed size. They're numeric data. We also have like other advantages, right? So it's very easy to label new images. It doesn't require expertise. Most people can look at these images of handwritten digits and tell you what it is and label it for you. So crowdsourcing works. It's also, there's very little ambiguity. Some of these might be kind of odd, but mostly when you look at these, you can work out what digit was intended to be written if you're somebody who's familiar with these digits, right? So these are, in some sense, straightforward problems where you can collect lots of data and we know how to represent it. In machine learning for molecules, if we have a molecular property prediction problem, there's a few big differences. So the first one is collecting data is often expensive and slow. So if we do have to run these simulations or run lab experiments to come up with data, we're often not going to have a lot of it. So we really are going to have to need to have machine learning models that are robust to dealing with the fact that we don't necessarily, we have complicated relationships that we'd like to model, but we don't necessarily have a whole lot of data available for any new property that we might be interested in testing for. And then, secondly, there's this whole problem where representing a molecule is non-obvious, right? There's many sort of choices for what's best, and they might depend on the different settings. And I'll come back to that in a moment as well. And also, since we're often running this in a setting where we are trying to close this loop in between running experiments or expensive simulations and using the machine learning model, we often are in a setting which is an active learning or a Bayesian optimization style setting where we are collecting labels while training the model. And so we have to somehow reason about which are the most informative labels to collect next and why. And doing so requires having models that have well-calibrated uncertainty estimates. So not just making a prediction, but have some notion of whether or not a particular point is one where it's making a good prediction or if it's actually very, very unconfident. There's also other challenges with this setting. So, if you take an image and change a small number of pixels in the image, it's still a picture of the same thing. It's, you might fool a classifier, but in general, small changes like modifying a few pixels or adding high frequency noise or something to a photo doesn't change fundamentally what label information might be for that photo. It would just change maybe some other image statistics. And that's kind of the principle for molecules as well. There's this basic QSAR principle, this quantitative structure activity relationship. And there is a relationship between the structure of a molecule and what it does. And it's locally kind of smooth, but there's this problem that's known as activity cliffs, where small structural changes can have large effects on the properties. So on the picture on the right, this is from a paper by Nadine Scheider and co-authors that looks at this problem of chiral cliffs. And these are situations where the only difference between one molecule and another might be something about its 3D structure and sort of how part of it is either rotated or conformed in space, but it has exactly the same constituent atoms with exactly the same graph connectivity in terms of what the bonds are. And this can have large effects, for example, between something being a useful drug versus something being toxic. There's also the example in the bottom is looking at data on how different molecules smell, looking at their odor. And many of these different molecules actually, they only have really small modifications to them, just maybe a couple atoms changed, but they have qualitatively different smell responses. So I guess with this all in mind, let's think about different sorts of ways of representing molecules. So there are a lot. I think a couple of them, a couple other ones than what I'll talk about will come up later in this session. For my purposes, I'm going to focus on thinking of molecules as a molecular graph. So in a molecular graph, you have a set of, so a graph is composed of nodes and edges. And the vertices or the nodes in these graphs are the non-hydrogen atoms. And the edges are bonds. There's maybe a few different bond types. These could be single bonds, double bonds, triple bonds. And the atoms, these nodes in these graphs, have a set of properties that are associated with them. So this can be, one thing is simply what type of atom is it? So for example, these are mostly carbon atoms, but there's one oxygen atom in this particular molecule. And also, other properties are sort of the charge of the atom or the number of hydrogens which are bonded to it. Molecules can also be represented as these sorts of smile strings. This is a useful representation, but I'm not going to talk about it here. So what do you do with the molecular graph? So most machine learning algorithms that we're used to take as input not a graph, they take as input a vector. So if you manage to turn your data into a useful vector, then all of a sudden you can rely on most machine learning methods. So here, so molecular fingerprints are one way of converting this molecular graph into a bit vector. And it does this by computing hashes. So it will take a bit vector that's very large, for example, maybe 2,000 long, like 2 to the 10, 2 to the 11. And it's so each bit in this bit vector corresponds to the presence or absence of a particular molecular feature. And it does this at a few different radiuses. So if you parameterize it by a radius 0, then it looks at every single atom that's in the graph and computes a hash function, an atom and its features, computes a hash of that atom, which gives you an integer, which modulo, say, 2048, if you have a 2048 bit vector, tells you whether or not that particular bit should be a 1. So for example, in this graph at radius 0, there's sulfurs, there's carbons, and there's oxygen. So all of those would be, correspond to positive bits. At radius 1, you consider these substructures that contain an atom and its neighbor and its neighbors, its immediate neighbors. And so then you hash that substructure, and then this gives you a different bit that corresponds to these, and so on. And so for drug design problems, for small molecule problems, typically radiuses of 2 or maybe 3 are kind of appropriate. And this gives you a large bit vector that corresponds to, is a particular structure present. This is a useful feature vector. For one, it's very easy to compute. There's toolkits that compute it automatically. It's computationally not expensive. And it works well in practice on a lot of problems. What it's not, though, is it's not dependent at all on the data. It's a completely fixed feature. It's not a learned representation. It's the same feature vector that you might learn for any sort of task. I mean, it has a few different parameters, maybe of what kind of radius you use and what your initial atom features are and so on. But fundamentally, it's not a learned feature. It's just something that is a hash of different substructures. But a way you can use this in a machine learning model is you say, well, I take my molecule and I run this molecule through my through the fingerprint, I compute a fingerprint of it, and then this can be an input to a machine learning model. So for example, a feed-forward multi-layer perceptron neural network model, or a linear model even, that then can predict some target property from data. So this is kind of a classic approach. It works quite nicely. But there is a sense that we're leaving something on the table here, because one thing that we've kind of seen in deep learning over and over is that when we can learn features from data, it's usually better. So one thing we can think about is what's sort of the deep learning alternative to these molecular fingerprints. And so something which is kind of analogous is to learn features using a graph neural network. And I'm going to kind of step through this algorithm for how you might compute updates in a graph neural network or a message passing neural network. So this kind of graph neural network computes per node features by first computing an initial feature vector at every node in the graph. And this initial feature vector is the same sorts of features that we saw for the fingerprints, right? So things like the atom type, maybe the hydrogen count, maybe other details such as its the degree or whether it's part of an aromatic ring. And what we now do is so that's a feature per atom. In order to get features that correspond to a radius of something greater than 0, so kind of analogous to the substructures that are an atom and its immediate neighbors, we compute incoming messages. So we define a trainable function. So these matrices A are learned parameters. And at the atom that's denoted by a 1 here, those features of that vertice are updated by looking at all of its neighbors and computing a linear transformation of the feature vector at its neighbors and summing it up. So the incoming messages into this node 1 are some kind of edge function of the neighbors at nodes 2 and nodes 3. So here, this is a different A matrix that we're multiplying by for each of the 2 different edge types, because one of these is a single or one of these is double bond. But there's many ways of parameterizing these. So there's but this is an example, and that gives us this sort of incoming message that's based off of the neighbors, and then we can update the features at this target node 1 by computing a function which depends on both the incoming messages, which is you can think of as a state update, like almost the way you would have a state update in a recurrent neural network, and the previous features at, the previous features are initial atom features here. So we take our atom features and we compute its incoming messages, and we run this through some nonlinear function. And then this gives us a new updated node feature. And this node feature after the update depends on, the node feature after the update depends on all the neighboring points. So we do this for every node, and this is one iteration of the graph neural network. And now we do this for every node simultaneously. And so these new features at each node in the graph are features which somehow capture information not just on the initial properties of that atom, but also on the properties of its immediate neighbors. And now what we actually do is we repeat steps 2 and 3, maybe a couple times. And every time you do this, you're computing new features that depend on the neighbor's features at every node. So if you run this once, your learned node feature depends just on your neighbors. If you do this twice, it depends on the neighbors and the neighbor's neighbors somewhat implicitly. And so you do this maybe a few iterations in order to capture the radius that is relevant for each. So that's a kind of hyperparameter that corresponds to the depth of your graph neural network, is how many iterations of this to run. And then, so this learns per node features, and there's methods for then collapsing that to a per graph or per molecule feature. The simplest one, which is really just fine, is to take a sum of all of your per node features. And what's important about the sum is it's permutation invariant. So it needs to be typically you want some permutation invariant feature here in order to collapse all of the features from the nodes into a single graph feature. So, however you may feel about this algorithm, this is an algorithm that kind of resembles the structure of computing these fingerprints that hashes local parts of the graph, except for now it's, instead of computing a bit that says the presence of a structure, it's computing a per structure feature. And then instead of putting all the bits into a bit vector, it puts a sum of all these features into a feature vector. So if you train this end to end, which you totally can, the first step is this message passing neural network that replaces the fingerprints. And then the second step is a feedforward network, which is basically the same kind of feedforward network that you have when running on fingerprints. So We call this feed-forward network the readout phase as opposed to the message passing phase of these graph neural networks. This is kind of the terminology that's traditionally used. So all right, so what should we do and why? Which of these is better? So, you might think, well, of course, the deep learning method is better. Let's definitely use the deep learning method. Why would we use these fixed descriptors if we're able to learn something? And, you might be right? So there's a bunch of papers which have introduced over the past maybe 5 years or so, have introduced different kinds of graph neural networks that expand on molecular fingerprints. And in general, these improve things, right? So I was looking at the predicting for a few different data sets. So a solubility data set, a drug efficiency data set, organic photovoltaics data set, and compared to the hand engineered features of these fingerprints plus a neural network, in these data sets, you see much better performance by doing these neural fingerprints or graph neural networks or graph convolutions followed by a network. And in some cases, this is a huge advantage. So on this QM9 data set, which is a data set with 130,000 molecules, and the targets are 13 properties approximated by quantum mechanical simulations, these are, it's actually a large difference. But there's a recent study from this year that went and actually kind of benchmarked these on a large number of both public and private data sets. And, the conclusion was, yes, these message passing neural networks are currently what you should use if you're making these property predictions in general. But it wasn't as unambiguous as you might think, in particular for these sort of small data sets. So if you filter to tasks, which, this is showing on the left a figure from the paper where they filtered to tasks that contain at least X molecules. And they found statistically significantly that the message passing neural networks outperformed the other methods, for sure once you got around like 1,000 some molecules in your training set, but less than that, that wasn't necessarily the case. And it also wasn't necessarily the case on data sets that were very class imbalanced. And so this suggests that there's settings in which the message passing neural network is not necessarily actually outperforming doing the sort of simple non-learned features. And unfortunately, that kind of matters, especially if we're thinking about settings where we might be doing active learning, where we'd have a small amount of data to start, then we really would like to be able to use the more powerful model. So I'm going to talk about two different things that kind of address these concerns. And these are two different workshop papers that were just presented at a NeurIPS workshop this year. So the first one is, how can we make graph neural networks worth it for low data molecular machine learning? And we're going to do this by thinking about a meta-learning approach. So for this, we're going to look at a data set called the Kemble 20 data set. It's a data set of molecules and experimentally measured properties. And we're going to filter this data set to only consider small tasks. So we're only going to consider the tasks that have between 64 and 1,024 data points. This leaves us with 645 distinct binary classification problems, which fall into 5 distinct task types as classified by the Kemble dataset. So ADME, these are pharmacokinetic studies, toxicity, binding affinities, functional, and unassigned, which is, I guess, a catch-all for the remaining tasks. And so we're going to split these tasks into training, validation, and test tasks. And then within each task, we're going to split it into training, validation, and test data. And we're going to do this in particular. So when we're going to see how well we can leverage some of these problems. So there's 645 problems. We're going to say, like, suppose we have small data sets on a lot of them. And now, some new task comes along where we would like to predict toxicity, but it's a new kind of prediction. Or we would like to predict a binding affinity, but it's a new target that we want to bind to. So these are problems which are somehow similar to problems we've already looked at. And we're actually considering maybe some of the same molecules, but we're considering a different test property. And so how can we kind of leverage the fact that there's this similarity between the tasks is the question. So we're filtering these tasks so that we have kind of in-sample and out-of-sample tasks. So we're going to train it using only a subset of the binding and the functional tasks. And we're going to test it then on the other types of tasks as well as on new binding and functional tasks. And here, this was just to verify, if we look at the performance of this ChemProp message passing neural network, which is the one that was in the benchmarking paper, and comparing it at varying data set size thresholds for Kemble, we see as well at around data sets of 1024 and up, the molecular fingerprints, the message passing neural network has the highest performance. But in data sets that are smaller, and in particular, the data sets that are less than 100 data points, there's actually still a large advantage to the feedforward network, to using the pre-trained fingerprints, the fixed fingerprints. So the approach that we took here is called meta-learning. So for meta-learning, the idea, so how can we do transfer, right? So one way to think about it is we say, well, if we have a whole bunch of tasks, we could try to evaluate a set of features which is simultaneously useful for all of these tasks. So this would be, for example, train one message passing neural network who is then able to predict values for all of the trained task targets. And so then when you go and try it out, then when you go and try it out on a new task, you have, hopefully those features are useful. The meta-learning approach is a little bit different than this kind of pre-training approach. So the meta-learning approach, instead we look to learn warm start initializations, which are just a few gradient steps away from good solutions for many different tasks. So this is a way of allowing fast task specialization, hopefully. So algorithmically, the way this works is we start with an initial set of parameters, theta, for our graph neural network and for our readout phase. And we run a small number of steps of gradient-based optimization on meta-trained tasks. So this takes our initialization and it updates the parameter, and we get a different parameter for each of the different meta-trained tasks that we're trying to estimate. And we compute the per task losses. And so each of these estimated parameters for the different tasks is going to be only slightly different than the initial set of parameters. But then what we do is something interesting. We take all of these losses and we compute the gradient back through the entire optimization procedure onto the initialization. So one step of this loop says, instead of optimizing the parameter for a particular task, we're going to optimize the initial point that allowed us to do a small number of gradient steps in order to update the parameter for that task. So this is our hope, is that this leads to learning a initial value theta over time, which is just somehow a small number of gradient steps away from perhaps diverse solutions in prediction space that handle many different tasks. And to be clear, the very last layer of this network, that's the actual output layer, is going to have to be trained per task. It's a question of the layers up until the output that are going to be specialized in sharing parameters. So we're going to consider a few methods here. So the first one is using the fixed fingerprints into a two-layer feedforward network. The second is a pre-training method where we jointly train a graph neural network on all of the different tasks that we're assumed to know sort of a priori, and then we fine-tune to test it on, given a new task, we're going to do a new task with a small amount of data, we're going to just do a small fine-tuning of the network weights and then hope that this leads us to something that somehow, by using this initialization, transfers well. And then the last three methods are meta-learning methods. So the first one is MAML, is the model-agnostic meta-learning that I just mentioned. First-order MAML, FO-MAML, is a cheaper approximation that avoids computing Hessian terms. And almost no interloop is another variant which skips the inner loop optimization entirely and instead just tries to learn features that just need the last output layer changed. I'm going to skip over the detailed results, but the overview is that MAML and first-order MAML actually perform really well. So if you take these and look at the average rank across both in distribution and out of distribution test tasks, then if MAML and first-order MAML both are, generally fall in the first or second range of the performance on these tasks. outperforming using the pre-trained fingerprints, outperforming, the fixed fingerprints, outperforming using a pre-trained network as a hot start initialization, and also outperforming this almost no inner loop algorithm, which doesn't do the sort of inner optimization meta stage. And we ran a statistical test on this to check whether or not this was significant, and indeed it is. So mammal and first order mammal were not significantly different, but they were all significantly improving across, improving upon the other methods. So in this sense, using model agnostic meta learning is able to actually make these graph neural networks outperform fixed fingerprints or pre-trained features in small data settings where otherwise, if you did not have access to these other tasks, you would have been better off not using deep learning and just using simpler features. So I think that's a nice result. I think it's useful, and I think it's worth investigating this further to see how well we can actually, use tasks where we do have a lot of data in order to help us out later on these other tasks where we might not necessarily. Something that's interesting here, where if you are familiar with this model agnostic meta learning algorithm, we saw something that was kind of interesting behavior relative to when people have run this before on image problems. So you can plot a canonical correlation analysis to see which layer weights are changing as you do this inner loop adaptation. So as you do this updates on your weights per task. And so in the paper that introduced the almost no inner loop algorithm, they motivated this algorithm, almost no inner loop, that just uses a shared feature by observing that mostly it was just the outer layer, output layer, that was changing, just the head node. The convolutional layers in their COMNet for processing images were almost always the same. This CCA measure was at almost 1, and it was just mostly in the head node. Whereas for us, we actually found that wasn't the case at all. So meta learning, rather than learning features that can be modified quickly, is very important relative to learning, say, a single set of features, neural fingerprints, that generalize well. And we can see that because we actually had low CCA similarity, particularly on the out of distribution tasks, not just in these last 2 layers here, which are the feed-forward network layers in the readout phase, but also in the parameters of the graph neural network, of the message passing layers themselves. So this is kind of qualitatively different than the results that people have seen before on meta learning on images. So I think other future work is to kind of investigate why, whether this is related to sort of distributional shift, whether this is related to something to do with the data, whether it's something to do with the properties themselves, etc. So that's, yeah. So the other thing that, yes?
So do you have any hint why this is happening? Or?
Yeah, so I think, I don't know. I mean, the fact that it's harder on the out of distribution tasks, I think, is sort of suggests that some of it is due to distributional shift. So I think a lot of the examples that were used for image classification were for few shot learning on new classes. So you train a classifier to look at images and identify particular classes, and then you show new classes. Then you show new images and ask for predicting a new image label. And I think it's in some sense just a more similar task in terms of what the features are. So particularly if you're going from predicting binding affinities to predicting toxicity or something, like you might just actually need kind of different features. So my guess is this sort of distributional shift has something to do with it, but I'm not quite sure. The other thing that's different relative to other meta learning settings for this mammal algorithm is we weren't really focused on few shot learning. So often these are done in a setting where you just have, say, one new data point and you would like to learn it that way, and you would like to do it in, say, one gradient step to do it fast. And we actually do have maybe data sets of up to 1,000, and we have a training set and a validation set, and we're willing to run as many gradient steps as necessary before our validation error stops going down. So we actually run much longer optimization routines as our inner loop than other papers that are examining this do. So that also might contribute to it. So I'm going to quickly present some other work on Bayesian graph neural networks. And this, so why be Bayesian about your graph neural network, and what are you going to get for this? This is because this distributional shift is also a problem. And so here's a quote from a paper, Robert Sheridan from 2013, that I thought was really interesting. So it said, Merck recently participated in a Kaggle competition to test our in-house QSAR methodology against other methods. We used a subset of the data sets discussed here and constructed training and validation sets by time split, by which they mean they took molecules that were measured in-house for a particular assay and split them by the ones they measured up until a different particular date and the ones measured after. We were surprised how many Kaggle contestants were puzzled by the fact that the distributions of the descriptors in the two different sets were different. The expectation seemed to be that A and B would be randomly selected from the same pool. And this is kind of a thing that we often miss. If you're looking at a molecule data set, you get a whole bunch of examples of, say, maybe positive or negative activities for a particular molecule. But these activities might have been collected at different times and for different reasons. For example, one of them might have been because you're testing a particular molecule for activity, or sorry, you're testing for a particular activity, whereas in other cases, maybe this assay is part of a control, or who knows, right? Also, just in general, if you're doing molecular design, then the molecules that you're kind of aiming to actually target might change over time. So you're going to naturally see a kind of distribution shift in terms of what the molecules are. So we can kind of simulate this by doing things like taking these molecules and clustering them. So you could cluster the training set and do non-random train test splits. You can also split based off of these molecular scaffolds. So you can take molecules that have the same sort of rough backbone or rough overall structure and partition your training and test data sets so that molecules with the same scaffold don't appear together. So this means you're always testing on molecules that are at least a bit more new than just small perturbations to existing ones. And this slightly better replicates this kind of time split behavior. And so to deal with this, to try to get some notion of the uncertainty, we're going to replace this typical deep learning approach where we find a single best setting of the model weights across the training data and then use these weights for predictions on new data by instead using a Bayesian approach to this. So instead of estimating a single best weight theta hat, we're going to estimate a probability distribution over weights, p theta, given our training data. And then when it's time to make predictions, instead of making a prediction by plugging in our best estimate theta, we're going to make a prediction by averaging over all of the different plausible weights in our neural network. And this gives us, this captures the uncertainty in the model much better. So this is particularly important for when we have small data sets where we might not have learned enough from the data yet in order to reduce our uncertainty about a property, or for out of distribution data relative to the training set, where you might expect your predictions to be very accurate on data that's similar to what you trained on, but on data that's far away, you might no longer think it would be so. And this way your model can kind of estimate this for you. So the challenge here is that inference in Bayesian neural networks is hard. So these are all a number of different algorithms for inference in Bayesian neural networks, and it's kind of out of scope to go through what they are, but characterizing this posterior is tricky. But there's a bunch of different approaches, and so we kind of looked at all of them to see how well they treated us. The main thing to note here is two of these, replacing the readout phase with the Gaussian process and adding MC dropout to the readout phase, only capture uncertainty in the feedforward neural network that processes the features at the end. Whereas these algorithms drop out everywhere, as well as SWA Gaussian, stochastic gradient longitudinal dynamics, Bayes by backprop, and depth uncertainty networks capture uncertainty in the message passing step as well. And so this kind of addresses a question on whether or not, in order to get well-calibrated uncertainties, do we just need uncertainty at the readout phase, or do we actually also need uncertainty in our feature computations? So we ran this on the QM9 data set, which I mentioned earlier. This is this large molecular regression data set with quantum mechanical targets. And we looked at the calibration of these methods. And interestingly, if you use Gaussian likelihoods, none of these methods performed very well in terms of their calibration of uncertainty, but they weren't overconfident. They were actually all kind of underconfident. And this is sort of, we think this is because they're they're overestimating the aleatoric uncertainty because there's some number of points where the predictions happen to be actually just very, very wrong. The mean prediction is quite far off. And so by using heavy-tailed likelihoods, student t likelihoods, then we found we had much better calibrations of uncertainties in the model. And we also found some of these methods worked better than others, which I'll show in a moment. We also tested this not just looking at sort of the calibration of the uncertainty, but also the performance of the uncertainties in an actual task. So here we were looking at a molecular search task where you start from a small number of initial data points, and then you collect labels for 50 new data points in every round. And you use both the uncertainty as well as the predictions in order to collect a diverse set of points at the next stage. So this is a task that requires having posterior distributions that are in some sense good. So if you have a better model for your network, then you'll see better results in this molecular search. So I realize I'm at time. So to clarify, so to sort of look at these results, one interesting thing we saw is that not all of these methods performed best on the same tasks. In fact, the top 3 were different. So in terms of looking at predictive accuracy on the QM9 task, which is a large data setting, we found that the sort of more complicated methods in some sense, so the SWA Gaussian, the stochastic gradient, MCMC, this mean field variational inference method, they performed, they had very accurate predictions, and they had very well calibrated uncertainties on QM9, whereas in the molecular search task, where you're starting from a small number of training examples, we actually saw better performance with the Gaussian process readouts or the dropout methods. And I don't actually know if this is something that's inherent to these methods, right? So I think some of it might just be the case that there's a lot fewer hyperparameters to tune for your Gaussian process model and for your dropout model. So it may be the case that for, say, when it comes time to estimate things like learning rates or so on, that it's simply these methods are sort of robust to bad things. So I think this requires more investigation as well. So my final thoughts here are, molecular machine learning can be hard, right? So data sets are small, molecules are sensitive to small changes, data set distributional shift is common. And these graphical networks can be really excellent property predictors. So I really recommend using them, but they are sometimes still outperformed by simple models. And it would be good to understand when and understand when we can fix that. Improving uncertainty quantification and investing in good approaches to transfer learning from using different related tasks where we do have more data for can help the reliability, especially in these low data settings. And so here I have links to these 2 workshop papers on arXiv, as well as these 2 MSc students who worked on these 2 projects of mine, who are responsible for a lot of this work. So thank you very much.
Thank you, Professor Page, for this nice talk. So there are several questions. I just, if you can take some of them. So there are a lot of people from chemistry background who are actually attending this talk. So there are some detailed chemistry questions which you can see that the phenyl lithium which you were showing in the initial things. So you can see in the Q&A that there are questions on this phenyl lithium, that why the fingerprints of atoms marked 1 different from atom next to 3. So for a chemist, these positions are considered to be same. So
this was on the molecular fingerprint image?
Yeah. This was on the molecular fingerprint image. So yeah, this may be detailed, but Ganesh, you want to make it a little bit more specific, if you want.
Yeah.
Anyway, I think you can take that.
Yeah, I don't think I have a specific answer for that. I think so. It also might depend on which features are included in the initial hash. So that's
so let us take a more generic questions. The atomic properties you showed were all chemical properties. To expand this representation of molecules to more types of problems, how can 3D structure properties of molecules be captured via graph neural network? So this is an issue which everybody is facing,
Yeah.
I think. So your
Yeah,
take
I
on
agree.
that.
I don't have a good answer for this. I actually have also been wondering about this, and everyone always kinds of asks it. I don't know. Actually, I see Miguel has joined us, and he might know something better. I mean, but the I mean, if you're working on graph neural networks like this, one way to do this is to change what your initial features are that go into your atom representations. And so you can include features that represent the bond angles in your initial atom representations, and that's one way of capturing it. The other thing that you can include, I think, is if you think about sort of, I guess you can include chirality as edge features as well. So this is also a way of incorporating it. But yeah, no, I don't have a good answer for that.
So the next question is there that means you did meta learning, it is done. So somebody is asking that whether multitask learning in addition to meta learning would have been good, like learning multiple tasks and
Yeah, so that's actually what the pre-training benchmark was, and we were sort of surprised it didn't work very well, right? So let me find this. Yeah, so the pre-training benchmark is kind of this, right? So we took all of the tasks that for the meta learning algorithm were the meta train and the meta validation tasks, and we trained one network that jointly predicts all of these target properties from the same graph neural network and the same readout phase up until the output layer. So this has, the last layer is different, but beyond that, they all have a shared feature representation. And so I guess we kind of thought that those would be pretty good, right? And we could take those and directly replace the output layer with an output layer for our new target, right? Like replace the head, and then maybe fine tune the weight slightly using in our meta task using a validation set. But in practice, it actually worked far less well. So there seems to be actually something important about the meta learning aspect here itself for this setting. I think that shows up in those CCA plots as well.
Sure. Yeah, so these are like complex things, and many things are not still understood that how things are working. Yeah, I think many people are trying to find out, and researchers are working on this. So thank you, Professor Page, for this wonderful talk, and thank you for accepting the invitation and being present here. So thank you.
Hey, thank you for having me.
In normal time, we could have given you a present, but now it's it's all.
Yeah, well, maybe I'll come visit.
Yeah, please, yeah, sure.
In 2 years or something. Yeah.
2 years.
Okay. Yeah, thank you very much.
Thank you. Okay. So, yeah, the next talk is by Dr. Jose Miguel Hernandez Lobato. So, Dr. Lobato is.
Yes.
Yeah.
I'm here, already connected.
So Dr. Lobato is a university lecturer equivalent to US assistant professor in machine learning at the Department of Engineering in University of Cambridge. So before this, he was a postdoctoral fellow in Harvard Intelligent Probabilistic Systems Group at Harvard University, working with Ryan Adams, and a postdoctoral research associate in the machine learning group of University of Cambridge, working with Jubin Gharamani. So Jose Miguel completed his PhD and MPhil in computer science at Computer Science Department in Universitat Autónoma de Madrid, where he also obtained a BSc in computer science from this institution with a special prize to the best academic record on graduates. So you were really son of the soil. So you did everything, BSc, MSc, PhD there. Jose Miguel's research focus on probabilistic machine learning with a particular interest in deep generative models, Bayesian optimization, approximate inference, Bayesian neural networks, and applications of these methods to the problem of automatic molecular design. Up to you. Over to you.
Good. Thanks for the nice introduction. I will share my slides. Good. I think they should be visible now. Can you confirm?
Yeah, it is visible. It is visible.
Great. So thanks a lot for inviting me. And I think it's been great to have this amazing talk by Brooks first, which gave a very good introduction to this topic. And today, what I'm going to describe is a collection of techniques that I have been working on with different people from my lab and different collaborators. And the idea is to use deep generative models for automated molecular design. Deep generative models can capture properties of existing molecules, and then they can be used to generate new molecules with improved properties. And the key thing is how to do this efficiently and in a way that you obtain molecules that are going to be useful in practice. And we are going to see today different techniques for addressing this problem. First of all, I would like to thank my collaborators in these different projects. The works that I'm going to present were done by some of the PhD students in my group, Austin Tripp, Eric Daxberger, and John Bradshaw. And this was also done in collaboration with really amazing scientists that include Matt Kunzner Brooks, who we just had a talk by him before this one, and Marvin Segler. So yeah, I'm very thankful to these great collaborators. Before getting into the detail, I would like to start with some motivation for the techniques that I'm going to be describing. It happens that many problems in science and engineering require us to optimize expensive black box objective functions. And these expensive functions, they receive as input a high-dimensional structured object. There are many different types of problems that fall into this category, but some very relevant ones appear in drug and material design. In this type of problems, the expensive black box objective is going to receive as input a description of a molecule. And the output is going to be some metric that indicates how useful that molecule is for a particular task. The molecule could be, for example, a drug, or it could be some organic photovoltaic that could be used to make more efficient solar panels, or some description of an organic lead for building better screens. So the black box will receive as input this structured object, the molecular compound, and the output is going to be an estimate of its properties. For example, for treating a disease, it could be a description of the efficacy of the drug. We might be interested in designing drugs that bind to specific targets, and we could have different metrics to assess this, from docking to more advanced simulations, and even to wet lab experiments. So obviously, evaluating those objective functions can be very time consuming. And the question is, how can we do this search over molecules with improved properties efficiently? In practice, this is highly challenging. And the reason for this is that the molecular space or chemical space is huge. There are many different possible molecules, and identifying the few molecules with useful properties among the many irrelevant ones is going to be very time consuming. So we would like to use methods that can guide our search for those improved molecules efficiently. Another thing that is important is that the space of molecules has also complicated constraints. We are not just interested in arbitrary molecules, but we are also interested in molecules that are realistic and similar to the existing ones. We want molecules that are easy to synthesize in practice, for example, molecules that are going to be stable and don't degrade, and so on. So the question is, how can we perform this search for realistic molecules efficiently? And one approach to do this, which was presented recently, involves using deep generative models. These models, they can be trained on existing data sets of molecules. They will capture the patterns and regularities present in already existing molecules, and then they will be able to generate new molecules with similar properties, but also different. So these newly generated molecules could have improved properties. And the question is how to use these models to search more efficiently for those realistic improved molecules. The models that I'm going to describe mainly could be understood as variation autoencoders, and they work as the figure shown here. These models, they are going to have an encoder neural network that will receive as input a description of a molecule, and it's going to map that molecule into some continuous latent space. This latent space is usually of low dimensionality. And then we have also another neural network called a decoder that is going to map points from this continuous latent space into the original input description of the molecule. So these things could be molecular graphs. The description of the molecules could be molecular graphs. They could be also text sequences encoding the graph as well. These sequences are called the Smiles strings. It doesn't really matter much what representation you use. But the key thing is that we have now this low-dimensional representation of the molecule, and we have some procedure to map molecules to this continuous low-dimensional latent space and to decode back. The interesting thing is that these models can be combined with a predictor from the latent space into properties of the molecules. And by doing so, you can then think of doing molecule optimization in a process that will involve mapping some initially promising molecule into the latent space, and then looking at the predictor that will estimate the properties of the molecules. And this is shown here. So we'll have like some latent space that is going to map into different points in this continuous latent space are going to map into different decoding molecules. And then we have a predictor for the property, and we could try to follow this predictor for the molecular property to improve our molecules and to move into regions of latent space that will decode into molecules with improved properties. This is a very simple optimization problem. If you are interested in doing it efficient so that you don't have to evaluate a lot of properties for different molecules, what you can do is to use data efficient optimization methods, such as Bayesian optimization methods. There are a collection of techniques called Bayesian optimization methods that will allow you to optimize efficiently expensive black box functions. And they work in a similar ways as I described here. You typically feed a probabilistic predictor for the output of the output of the black box function, and then you use the predictions of this predictor to make intelligent decisions about what points to evaluate next, so that you find the inputs with highest objective value fast. So the advantage of this approach, based on the deep generative models with this continuous latent space, is that you can now perform the optimization in the continuous latent space. You can use existing methods for solving this type of optimizations. For example, you can use right away Bayesian optimization methods. You also avoid working directly with a high dimensional input space. You work in a lower dimensional space. And also the generated points, because you are using the decoder that was trained by looking at existing data sets of molecules, the generated points by these methods will exhibit similar properties as those molecules found in the training set. This means that if we want our molecules to be stable, for example, this is likely to happen because the molecules that these models will generate will be similar to those found in the training data. So this sounds great, and it's a very exciting research area. However, this approach still has some limitations. And in this talk, I'm going to describe some new contributions trying to improve these techniques for efficient molecular optimization using deep generative models. The first contribution that I'm going to describe was recently accepted at NeurIPS, and it's a method called weighted retraining that will improve the performance of this approach. And I'm going to describe this method. This was done in collaboration with my PhD students, Austin Tripp and Eric Daxberger, and both of them were equal contributors in this work. So what are some of the limitations of this approach that does molecular optimization in the latent space of deep generative models? We call this approach, by the way, latent space optimization. One of the limitations is that typically the way these models were used before is that you had some initial data set of molecules, and you could train the generative model on that data set. And then once you have trained the model, you have a mapping from molecule to latent space and from latent space into molecule. And the model was not really retrained after collecting new data. This creates problems, and this is illustrated in this example. No? We have some original input space, calligraphic X, shown here. This could be the space of molecules, and it's mapped into some lower dimensional latent space set. And it may happen that the model has been trained only on molecules that have suboptimal properties. There is here a promising region of input space shown in green that contains molecules with high property values. And there is one particular point with the best property value shown by this yellow star. But our model didn't include data in that region. And when we train our model and we just not update the model as we collect more data, it may happen that the model may be able to generate new points, but those points that can be generated by the model are those laying in this region described by this discontinuous line, and we won't be able to really extrapolate into these promising other areas of this promising region shown in green, and we won't be able to reach the yellow point. So this can be problematic. So what can happen is that this approach for latent space optimization is not going to be able to find an optimum line far away from the training data if we don't really retrain the models. So that's fine. You could think of retraining the models, but even if the model is retrained, you may have trained your model on a massive data set of existing molecules in an unsupervised way, and you may collect a few new data points corresponding to molecules with improved properties. This may be only a few data points. It could be on the order of tens of molecules, or maybe hundreds at most. But the new data is much smaller compared to the original data that was used to train the model, which could contain hundreds of thousands of molecules. So the new data is going to have a diminishing effect, and actually it's not going to really change our generative model much. So even if we retrain the model using the newly collected data, then we will run into problems. So what we propose here to address these limitations is first, we're going to retrain the model, as I mentioned, to avoid the problem of being constrained to suboptimal regions of the input space. But to address the problem of the new data having a diminishing effect, what we're going to do is to weight the data. In particular, what we're going to do is going to retrain the models, but using a weighting function that will focus more on the data points with improved objective values. And this is going to be key to improve the performance of these models. The idea is now, instead of having a generative model that is going to focus on describing each molecule equally, we're going to focus on describing molecules with better properties. We're going to focus more on those molecules with better properties and less on those with less properties. But we will still care about the molecules with worse properties, because the patterns and regularities present in those molecules could be still useful. So how does this work? We called our method weighted retraining. And the idea is that we are going to retrain now our generative model after collecting new data. In fact, every new 50 data points that we collect, after collecting 50 data points, we're going to retrain the model. And now when we retrain the model, instead of using all the available data that we have, It could be the unlabeled data that we used at the beginning, and then the newly labeled data. We're going to use all this data, but we're going to weight the data according to the quality of the objective value that we may have for that data. So in particular, we're going to use this following weighting function, which includes this quantity k, which is going to be a hyperparameter that controls the amount of weighting, and is the total number of data points in our data set. And then we have here the rank, which represents the rank of the data point according to the objective value available for that data. So the properties of this weighting function are as follows. In particular, for different values of k, we will be able to control the amount of weighting as follows. If k is very large, what is going to happen is that our weighting function is going to be uniform. If k is very large, this rank value here is not going to have a significant effect. And then all the different molecules are going to have similar weights. If k is equal to 0, then what is going to happen is that all the weight is going to be placed on the single molecule with the best value. So this rank is basically the rank of the molecules according to the objective value that we have for that molecule. And you can imagine that the best molecule is going to have rank 1, and the worst molecule is going to have rank n. So, and we are subtracting here 1. So whenever k is 0, then the first molecule, the best molecule, is going to have rank 1, and then we are going to have here 1 over 0, which is going to be infinity, and then we're going to have a huge weight on the single best molecule. And when k is, again, very large, then this rank metric is going to be at least n, and that could be much smaller than this quantity. So we have this weighting function. And this illustrates how we can control now the sampling distribution of the data if we sample the data with probability proportional to these weights. What is going to happen is that, for example, for large values of k, the weighting of the data is more or less uniform. And we see that the weighted and unweighted data have similar distributions. Each data point has the same weight. And as we reduce the value of k, we switch our weights to be larger for those molecules with higher objective values. So here the x-axis is the objective values of the different molecules. And we see that for smaller values of k, we are giving more weight to those molecules with improved objective values. And as we make k smaller and smaller, we focus more on those improved molecules. Good. So by changing the value of k, we can then change our weights over the available data, and we can focus on molecules with better objective values. The interesting thing is that this weighting function that I described here is more or less independent of the number of data points when this product, k times n, is larger than 1. This means that whenever you have a large number of data points, then this product will typically be larger than 1, and then the weighting function is going to be independent of the number of data points. So you can then ignore this quantity n in your weighting function, and you can just focus on choosing a value for this hyperparameter k. This is illustrated here by this plot. You have on the x-axis the data fraction that we are considering at the moment, ranked according to the objective value. And then here we see the cumulative weight fraction when we use our weighting function. And we see that when k is relatively large, in this case is 1, the weighting function is more or less uniform, so there is not much change. This is close to the identity function, the blue line. And what is interesting is that you obtain the same cumulative weight fraction for different number of data points. If you use 1,000 data points or 100,000, it's more or less the same. The same happens if you decrease the value of k. If you choose a value of k that is 10 to the minus 2, this is low, closer to 0, and then we give higher weight to those molecules with improved objectives. We see that here we are given higher value to those improved molecules with better objective values. And again, the curve that we obtain is similar for both 1,000 or 100,000 molecules. The two plots actually overlap with each other. So this shows that actually we can ignore the number of data points in this weighting function, and we can then just focus on the parameter k. What happens is that values that are relatively close to 0 will increase the weighting. And in practice, what we found is that a value of k equal to 10 to the minus 3, when you have about thousands of molecules, then this works fine for the reweighting. So we're going to use in practice values of k close to 10 to the minus 3. So how does this approach work in practice? What we find is that with weighted retraining, before we were limited to exploring this region given by the dashed line of the input space. Now we are going to be collecting data points in the region that has good properties. We're going to retrain the model, and we're going to reweight those data points with a higher weight. And it's going to make our latent space to give more focus into this region with improved properties, and will allow us to find better molecules. So how does this work? Yes?
Dr. Vato, there is a question just, I thought it is relevant, that what does the objective function used to determine the, what is the object used to determine the rank of molecules look like? So that is a question.
This will be the property that you are interested in optimizing. It could be, for example, if you are working with the design of OLEDs, organic LEDs, it could be an estimate of the power conversion efficiency given by quantum chemical simulations.
Sure, please. I think this is fine. Yeah.
Good. So how does this work in practice? We first tested this on a toy problem. The problem here is to do some optimization over some high-dimensional structured space. This is a space that contains square shapes. We start with an initial data set with about 250,000 square shapes, as shown here. They appear of different sizes and in different angles of rotation. And our goal is now to maximize the shape or the area of the shapes generated by our model. We're going to train a convolutional variation autoencoder on this data set. It's going to generate new square shapes, and we're going to focus on maximizing the area of these shapes. We're going to collect 500 new data points, and we're going to perform we're going to retrain every 50 new data points. This figure shows here in pink, we have the distribution of objective values on the training data. This is a violin plot, and we see that there are many data points with low objective values, and a few ones have higher. Then we show the result of the data generated after weighting the data. This is shown in gray. We show the result of a variational autoencoder model that is trained with a weighting function on the available training data. And we see that now, as we increase the amount of weighting on those molecules with improved objective values, the distribution in gray switches to generate more values with good objective values. We cannot still extrapolate beyond the original training data. We see that we don't really get much better objective values than those in the training set. And then we see after the optimization of 500, after collecting 500 data points, when we retrain our model, we show the distribution of the data points generated by the model, the distribution of objective values. And we see that as we increase the amount of weighting, we actually obtain much better values. Especially when we use this value that I mentioned before, 10 to the minus 3, things work quite well. And this curve shows here how it works in terms of the objective values that we collect. On the x-axis, we have the number of evaluations, and on the y-axis, we have the best value found so far. And we see that weighted retraining outperforms significantly other methods that involve not weighting the model, but retraining it, or weighting the model and not retraining it, or just using the initial generative model that was fed to the original training data. So that was for generating square shapes. We also tested this on optimizing some particular molecular property. In this case, we look at the log P score. which is related to the solubility of molecules. We have some initial data, about 250,000 molecules from the zinc database, and we use a junction tree variation autoencoder model. We use a weighting function with k equal to 10 to the minus 3, and we're going to do optimization in the latent space using the sparse GPs as our predictor. And we see here, as a function of the number of evaluations, the best value collected so far. And we see that, again, weighted retraining outperforms by a huge margin other baselines that do not do the weighted function, or they don't retrain the model. So to conclude this part of the talk, we have seen here weighted retraining, which is an approach for latent space optimization that results in latent spaces that are highly useful for optimization. Optimization in this case is easier. The method is actually very simple and easy to implement. You just have to retrain your model and weight your data. And we have seen that this significantly improves data efficiency and final performance. So this concludes. Yeah.
So there is a question, perhaps you can take.
Yes.
So there's a question, could you elaborate on the data used while retraining, and how is it different from the ones used for training before?
It's exactly the same data. The only difference is that you have new data points corresponding to the new molecules that the model generated and that you use to call the black box function.
So then next question would be then why this reweighting helps, means why the new data?
Yeah, so the weighting helps because you could imagine that in this data set with molecules, we have 250,000 molecules in our initial training set, and this is a very large data set. And we are going to collect only 500 new molecules. So if you collect only 500 new molecules, the weight or the contribution of those 500 molecules compared to the 250,000 that you had before is very small. This means that the model is going to focus a lot. If you don't do weighting, the model will focus a lot on describing these molecules with worse objective values. And it's not going to focus much on the newly collected data points that have better properties. When you weight your training data, you give more weight to those molecules with improved objective values, and then the model is not going to focus so much on the other large amount of data that has worse properties.
Sure, I think that answers the question. Yeah, please go ahead.
Good. I'm going to move now to the next part of the talk. And now this is going to address another limitation of these deep generative models of molecules. And this is a paper presented recently also at New Rips. And this was a joint work with John Bradshaw, who is a PhD student in my group, and also with Brooks. We just had a talk by him. Matt Kunzner, who is a faculty at UCL as well, and Marvin Segler, who is now a research scientist at Microsoft. Good. So in this case, the limitation that we are addressing is that existing deep generative models of molecules focus mainly on generating molecular graphs. So they generate molecules in this way. They will just output graphs directly. But these graphs may not be useful in practice, in particular if you cannot really synthesize those molecules. So ideally, we want generative models that will generate molecules in the same way that we would do in practice via chemical reactions. We want models that will generate, for example, a particular product molecule by telling you some initial reactants that you could use to obtain the final product. The advantage of this approach to generate molecules via chemical reactions is that the generated molecules will be more likely to be synthesizable in practice because they're actually generated in the same way as you would be synthesizing them. The synthesis information is available right away, and this could be useful, for example, if you want to maybe account for different aspects of the synthesis process when you optimize for your molecules. And the generated molecules will exhibit also more realistic properties. For example, they will have improved stability. The approaches that just generate molecular graphs may generate structures that may be less realistic than those that are generated by chemical reactions. Good. So how can we do this in practice? What we propose is an approach in which we are going to generate a multi-step reaction. And this multi-step reaction will be encoded as a directed acyclic graph. And this is shown here as an example with a paracetamol. This is the synthetic route for paracetamol. You start with some initial building blocks or starting materials, and then you obtain some intermediate products, and at the end you obtain some final product. So what we are going to have now is a generative model that is going to actually generate this type of directed acyclic graphs. These are directed acyclic graphs of molecular graphs because each node in our graph is a molecular graph on its own. And we call these DAGs of molecular graphs dogs. And our model is actually called dog because of this. To train this model, we are going to use a data set that contains synthetic roots for existing molecules. And this data set was derived from the USPTO dataset, which contains synthesis data from extracted from the US Patent Office. We have about 70,000 synthesis DAGs in this dataset. So the way the model works is we are going to generate these synthesis DAGs by serializing them. We are going to write them sequentially, the different elements. Those elements are going to be building block nodes, intermediate product nodes, and then edges connecting each of these. I'm going to describe here with an example how we generate these synthesis graphs sequentially. So we have this target DAG, the one that will be generated by our model. And the way we generate this DAG is as follows. We start by choosing some initial building block. This is the action taken by our model. We start always by choosing an initial empty building block node. Then we determine what is the content of this building block node. It's going to be this molecular graph. The next action could be, for example, to add another building block node. And then we have to choose the content of this, which is also done by the model. The next action could be to say, now instead of a building block node, construct an intermediate product node. We can then decide which already existing nodes in our DAG, intermediate DAG, we can connect our intermediate product node to. We decide to connect it to this building block node. We also decide to connect it to this previous one. And then once we have done this, we can decide to stop the connection of the intermediate product node. And then the next step is going to be to generate the content of this intermediate product node. And this is actually a different problem. It's a problem of reaction prediction. And there are already existing methods available for solving this problem. And we actually use those methods. One of them is the molecular transformer. This is a model that is going to map initial reactants into a final product. And our method actually uses the molecular transformer as an intermediate tool. So once we have the intermediate node, the next action could be to add another building block, determine its content, another intermediate product node, determine which nodes we are connecting it to, and then to specify its content as well. And then another building block node, its content, another product node. And here we just say we stop at this point and we just connect the final intermediate product node with all nodes that already have no descendants in the node, in the graph, which would be this building block node and this intermediate product node. No? So these are the nodes with non-descendants, and those are connected to the final product. So that's how we generate this synthesis graph. In practice, the key thing is how to generate these sequences of actions that are going to generate sequentially the synthesis graph. And we do that by using an autoregressive model. This autoregressive model is going to determine what action we should choose next as a function of the previous actions that we have taken. In In practice, this is implemented using a recurrent neural network because this is sequential data. And the recurrent neural network is going to summarize into its state whatever we have done before. And to make this recurrent neural network aware of the content of the synthesis DAG that we are generating at the moment, we are using graph neural networks. Brooks gave just before me a very good introduction to graph neural networks, so you are familiar with this. So this is how it would work in practice. We may have some initial input, which could be the location in latent space that we are conditioning to. Then we have our RNN that could receive as input the initial action. This could be just to add an initial building block because we always start with that action. And then the next action is to select the content of that building block. And we could choose this one. This is done by a specific action network that chooses between building blocks. The next step is going to determine if we add another building block node or an intermediate product node. We're going to have another network that is going to determine the probabilities of these actions. The recurrent neural network is going to receive an embedding of the previous action and also some description of the partial synthesis DAG that we have generated so far. We choose to add a new building block node, and then we have to choose its content. We cannot choose graphs that we have already chosen before. So the previous building block node the value of the previous building block node that we chose, we cannot use it again. So we mask out some of these elements. We choose that one and then determine the next action, which could be to choose an intermediate product node to generate next. And then we have to choose to which nodes that already exist in the graph we connect that node to. And obviously, we could also decide to stop connecting that intermediate product node to other nodes. And so on. This illustrates more or less the process for generating sequentially these synthesis DAGs. So what is interesting is that when we train these models, we already have the content of the intermediate product nodes, so we don't really have to worry about that. But later, when we generate data from this model, we need to generate the content of those intermediate product nodes. And we are going to do that by calling the molecular transformer. So based on this model, we actually propose two techniques. One actually uses the latent space as input, and this is going to be a variation autoencoder model. Another model just doesn't include this latent space, and we just generate data. This is an autoregressive model to generate the synthesis DAGs, and it's not doing any form of dimensionality reduction. So we have DocGen, which is the autoregressive model. It's a neural network that can generate now this type of synthesis DAGs, and it can actually be used for molecule optimization as follows. This is similar to the weighted approach that I mentioned before. You can feed your model to existing data, and then use your model to generate new molecules and take the best ones in terms of their objective value, and then retrain the model on those best molecules, and then generate molecules again, and so on. When you do this process of generation and retraining, you actually end up with a model that generates improved molecules. And you could use this type of models for molecular optimization in that way. The disadvantage of this approach is that it's not data efficient as a Bayesian optimization in the latent space, but it's still one way to do molecular optimization. And the other approach is to use our generative model as an autoencoder. We have an encoder network that maps molecules to the latent space and a decoder network that maps points in the latent space into the DAGs. When we use this autoencoder model, we can actually explore the latent space. We can map data points from the latent space, like this synthesis DAG, into latent space and then decode, and we obtain the same graph. This occurs most of the times, but sometimes it doesn't. In this case, it happens, and we actually can move in latent space, making small steps, following a random walk, and we end up with similar synthesis DAGs, but that are slightly different. For example, this one includes another building block node here that changes the final product, which is similar to the original one, but it's slightly different because it presents some of its unique characteristics. If we follow a random walk in the space, we obtain similar synthesis DAGs with their unique differences, but they present similarities with the original one. This shows that the latent space in this case is having some continuity in terms of the structures that you can generate. Good, so we tested these methods for molecule optimization. We followed the approach that I described before, where we just feed the model to the data, select the best molecules, retrain on those best molecules, and generate again. This is often called the cross-entropy method for optimization. And here we look at the quality of the generated molecules in terms of some metric called the Freshet-Chemnet distance. This is similar to the inception score that is used to evaluate the quality of the samples generated by GANs. Here, lower is better, and we have that our model generates molecules with similar metrics as some of the existing best previous models, which is interesting because the previous models are more flexible. They are not constrained to generate molecules via chemical reactions, so they are more flexible, but we are able to generate molecules as good as those ones. We also look at the quality filters of the molecules generated by our models. These are quality filters from the Whack-A-Mole benchmark, and they represent how stable, for example, or reactive the molecules are. And here, higher is better, and we see that we are comparable to some of the previous models that are performing best previously in this benchmark. So our model is able to generate high-quality molecules. We also tested on molecule optimization across different tasks from the Whack-A-Mole benchmark. Here, the goal is to generate molecules that are similar to a target one. And again, the best, the metric of the best molecule in the training set is shown with this discontinuous line. And we show that our method, shown in dark green, can improve over the training set, and it obtains similar values to those generated by previous baselines, which are not constrained to generate synthesizable molecules. So this is quite interesting. Sometimes we do worse, but in other baselines, in other benchmarks, we do comparable. What is very interesting is that when you look at the properties of the optimized molecules, we actually obtain optimal molecules that have a higher degree of synthesability as measured with a retrosynthesis tool. This is a tool that tries to, given a particular molecule, this tool, given a particular molecule, it's going to try to find a synthesis route for that molecule using some search. And obviously, if the molecule is not very realistic, you won't be able to search to find such synthetic route. What we find is that the optimal molecules generated by our model have a higher degree of synthesability than those generated by other models. And when we look at the quality filters of the optimal molecules generated by our model, also we obtain better values than those generated by other baselines. So to conclude, I have presented here a doc, which is a generative model for molecules that generates synthesizable molecules up front. It generates molecules via chemical reactions. It works by generating these molecular synthesis DAGs in a serial way, and it obtains competitive results in molecule generation and optimization in existing benchmarks. But what is really interesting is that our optimal molecules have higher degrees of stability and synthesizability as measured by this retrosynthesis tool and the quality filters of Whack-A-Mole. So that's all. This concludes my talk, and I would be very happy to answer any questions.
Great talk, Jose. That's a great talk. Yeah. So there are some questions from the audience. So one is the general question is that, can we do the inverse problem that given a molecule generate the synthesized path?
Yeah, so this is what the retrosynthesis tools do. And the challenge here is that you have to do some form of brute force search. So you will have to start with what are your initial starting materials. what are your collection of chemical reactions to transform those starting materials into new products. And then you will have to do some search over this space. And it may be that the search is satisfactory or not. So obviously, if you generate a molecule that is not realistic, or it has some patterns that are very different from existing ones, it could be that it's not this search is not successful.
Sure, sure. Yeah. So then there is a question of like, so the input to the autoencoder is smile. So this is a problem of smile notation, I think, that how structural difference is dealt with, or it's not dealt with such the.
Yeah. So for the input of our autoencoder is we use the molecular graphs. So the input to our autoencoder is going to be the synthesis DAG. So it's going to be this tree with this form of tree with different nodes, and each node is going to be a molecular graph on its own. And our encoder network is going to map this into some continuous representation. And for doing that, what we have is graph neural networks that operate at the node level. They operate on each molecular graph inside of these nodes. And then we have another graph neural network that operates at the synthesis DAG level.
Sure. Yeah. So I will just open the floor for the panelist. So anybody from the panel wants to ask something? Okay, so I have another question is of the retraining question. So the retraining has very deep impact, perhaps, like you have a lot of silver data and then you bring in some gold, small amount of gold data, and how to really leverage those gold data and get better results. Means there can be a generalized like generalized application beyond molecules and beyond.
Yeah, that's right. So that method actually can be used to do structured, high-dimensional structured optimization. And it doesn't have to be focused only on molecules. So we have this example with the images of square shapes. We have also another example that I didn't include in the presentation, where you optimize sequences of arithmetic expressions. So if you have a particular objective and you could do some efficient search for new elements in this highly dimensional structured input domain, then this can be a useful technique.
Sure. So there is a last question. I think we can take this. How is this action embedding created? So this is again a detail.
Yeah, this is like, I mean, the actions that we take are discrete. So this is just the same way you do embeddings in other problems that operate on discrete sequences, like the same way that you could do like an embedding of words, like words embeddings. You will have some you will just have some continuous vector representing the actions, and this is also optimized. So for example, here in this plot, you just have like a vector representing the action that you took. This yellow vector would be the action to generate to add a building block node, and this action might be that you chose a particular molecule to add. This is again the same as adding the building block node. So this represents the molecule that we added, and yeah, and so on. So you just have like continuous vectors describing the actions that you took in the past, or the actions that you can take.
I think that's so. Thank you, Dr. Lobato. This is a great talk, and yeah, so 2 new RIPS paper in one. So congratulations for that also. And
Thanks.
you know, I think this was very, very useful and very, very eye-opening. Thank you.
Good. Thanks again for inviting me, and yeah, I'm really enjoying the symposium.
Thank you. Sure. So the next talk would be by Dr. Christoph Schutt. Hi, Dr. Schutt.
Hello.
Hello. Yeah, hello. Yeah, thanks for accepting the invitation. So Dr. Schutt will talk about unifying machine learning and quantum chemistry with deep neural networks. So we'll see a different sort of integration here. And just to give a little bit of background, Dr. Schutt, I think I'm making your, my pronunciation is not right, perhaps. Is a senior, sorry about that. Yeah.
It's okay.
So is a senior researcher at Berlin Institute for the Foundations of Learning and Data, bifold. He received his master's degree in computer science in 2012 and his PhD degree from Technische University Berlin in 2018. And until September 2020, he worked at Audetic company developing neural networks for real-time speech enhancement. His research interests include interpretable neural networks, representation learning, generative models, and machine learning applications in quantum chemistry. Over to you, Dr. Schultz.
Yeah, thank you for the nice introduction and for the invitation. Yeah, so my talk is about unifying machine learning and quantum chemistry. And yeah, so this has a lot of similarities with the previous two talks, but also a different twist, as you will see in the first few slides. So my motivation slide is basically the same, right? We want to explore chemical space. We want to find new drugs, molecules for food processing, and all kinds of materials for solar cells, batteries, or catalysis. And I always like to show this plot that you can always get the news version on Wikipedia from the National Renewable Energy Laboratory, where you see the progress on the efficiency of solar cells. And you really see it takes decades to improve. And the ultimate aim here is to speed up this exploration process and get quicker to molecules and materials with some desired properties. So this slide I just inserted during Brooks' talk to really point out what the different approach here is. So what do we actually want to do with the molecules? Well, we want to predict properties for high throughput screening that you basically saw before. We want to generate molecules with desired properties, but we also want to simulate the molecular dynamics. So we want to get spectrum. We want to do virtual molecular spectroscopy, and we want to model the behavior of a molecule in a solvent. We want to simulate reactions to get the reaction barriers. And there you see this can't really be done with a graph. So as a contrast in this talk, molecules are not just graphs, but sets of atoms that are described by their atomic number and their 3D coordinate. So because if you want to actually model how the molecules are wiggling around, then you can't just do it with a graph, but you need the embedding in 3D space. So what's the idea here? So machine learning for quantum chemistry really gained popularity, I think, about 10 years ago as a topic. And the idea was, given the coordinate of the atoms and the atom types, can we directly predict the result of the Schrödinger equation? And you see on the left side, the Schrödinger equation is this harmlessly looking equation where you have the Hamiltonian operator H, then you have the wave function, and then on the other side of the equation you have the energy and the wave function. So it's basically an eigenvalue problem. However, it's not that harmless, and if you really look at the methods to solve it, so on the bottom here, full CI scales with n factorial, which is basically the numeric solution of the Schrödinger equation. So that's not good. So there are a lot of approximations that you can use. And one of the commonly used approximations is density functional theory, because it scales fairly well with n to the power of 3 to 4. But still, it takes quite some time to calculate these properties. So the idea is here, as illustrated on the left, you have your quantum mechanics code. Then you have to solve the Schrödinger equation to get the wave function in some kind of representation. And then if you have that, it's relatively fast comparatively to get the different properties that you then use to train your machine learning models. And then you can use your machine learning models to basically shortcut this whole slow process and directly get you to your properties from your structure. And really the core message of this talk is that beyond doing this kind of one-way prediction where we train a model to go from the 3D geometry of a molecule to some property, we see a trend actually, and there's some early work going into the direction that machine learning becomes part, on the one hand, of the quantum mechanics, its calculations itself, and on the other hand, also on all kinds of simulation workflows that you use in quantum chemistry. And then then we have the big topic of inverse design. So because even if we really speed up our calculations, we still have a huge space to explore, and we can't do that exhaustively even with the fastest machine learning model. So we have to go the other way around. We have to start from the properties and then predict structures that possess them. And I'm going to talk about a couple of models we developed in our lab that fit into these three categories. And yeah, first of all, I will introduce the Schnedt model to you, which is what I did my PhD about and where it all started for me. So perhaps, not perhaps, because you definitely heard about message passing neural networks in Brooks' talk. And back in 2017, in parallel to the message passing neural networks paper, we developed this Schnedt model that mathematically does something really similar, but has a different idea of what it actually does. So perhaps let me explain. So we have our molecule, like here, this ethanol, described by two sets of, or two tuples here. One is the atomic number that describes the atom type, so carbon, hydrogen, oxygen, and so on. And the other one is the position in space, R. And the idea was now to model this as a convolutional neural network. So in the beginning, we have an embedding layer where each atom type is assigned an embedding in a feature space. So in this case, we used 64 features here. And then we have these interaction blocks. And really, the important part that happens in these interaction blocks is a convolution. So we say, okay, we have our atoms in space, and now instead of having pixels like we have in an image, they are not aligned on a grid, but they can be at any position. So we could just apply a convolution over the space, and if we do it, and our convolution filter here is on a grid, we would get something like this. Because if we move our atoms around, so if the geometry of the molecule changes, we get these discontinuities here. And so the conclusion was to use a continuous filter instead. So something like this here. And we also said, okay, if the molecule is rotating, we don't want to the value to change. So we need radial filters to ensure rotational invariance. And so from this discrete convolution here, we go to the convolution with a continuous filter. And you see here the filter is modeled with a neural network that depends on Ri minus Rj, where in this case Ri is the center atom, Rj is some neighboring atom, and to make this radial filter, we just use the distance here. And if you do this a couple of times, you get your final features per atom that you then put into some fully connected network, and in the end you sum over these atomic contributions to obtain, in this case, the prediction of the energy of the atom. Okay, and we could apply this to different settings. So one setting is chemical compound space. So we have a data set of diverse organic molecules. These are in equilibrium, so they are stable. They basically at 0 Kelvin, they wouldn't move around. And yeah, you see what normally you see this chemical accuracy as a target to predict and these kinds of tasks, which is at 1 kcal or 0.043 electron volt here, and we got below this point with our models. And here, this is the part that you couldn't do with a graph, which is molecular dynamics. So if you have the energy, you can obtain the force that acts on each atom. So you can actually simulate the movement of the atom and then calculate different dynamical properties. Here, this is a radial distribution function for this fullerene molecule. And in this case, we could speed up the simulation time that would have taken 7 years with the reference method, that was DFT, up to 7 hours. So you see, even for such a small molecule, we can get huge improvements in the simulation in terms of speed. And of course, the larger the molecule gets, the more drastic you will see an acceleration. Right, and we also had a look at these embeddings that we learned, and we saw that we actually, so in this case, we trained on 60,000 crystals from the Materials Project dataset. We saw that there is actually some structure in the embeddings we learn. And so these are the first 2 principal components. And you see there is some kind of structure here where the atom embeddings are grouped, at least to some part, similar to the groups of the periodic table. And this is, of course, not in the data because the embeddings are just 1 hot encodings initially, and the embeddings are learned. So this is just learned from the energies and the geometries. Okay, and if you want to actually try this out, we have a software package called Schnettberg that you can find under this domain. Okay, but now let's see how we get to the part where we actually unify machine learning and quantum chemistry. So what I've shown you now is basically the classic approach. We generate some reference data and use it for training or machine learning models. So the idea we had now in I think shortly after we developed Schnet, is how to actually get to the electronic property. So how to get the wave function, how to get to the electron density. And then we said, okay, can't we just predict the wave function itself and then just obtain the properties from that? So, because if you do that, you suddenly have access to a wealth of properties, and you don't need a separate model for each one. So now our quantum mechanics code again is used to get the wave function, but now the wave function itself is a reference data, and we try to predict the wave function with machine learning. And to understand what we actually did, I have to unfortunately explain a bit about how you solve the Schrödinger equation. And what you see here is, so this is not, yeah.
Sorry, there is a question also on Schrödinger equation.
Yeah.
So would we need different functions to define Schrödinger equations of different dimensions, or would one function be enough? I just told you when you're talking, maybe you can also take this question. Yeah.
Of different dimensions. So in this case, we did this for molecules, for molecular wave functions, and that are specifically defined in a spherical harmonics, or let's say in an atom-centered basis. It really depends in which basis you represent your Hamiltonian, your Hamiltonian and your wave function. I think I will get to that in a bit. So here you see the Hamiltonian operator, which consists of the kinetic energy of the electrons, the electron nuclear repulsion, attraction, which is basically the force between the nuclei and the electrons that are around it. And then you have the electron repulsion. And the first problem here is that the position of the electrons are not known. Maybe you heard about Heisenberg's uncertainty principle, but they are described by the wave function. And so you can see, so the squared magnitude of the wave function can be interpreted as a probability density of the location of an electron. So that's why this is not just a matrix where you can just diagonalize it and you're done, because your operator actually depends on the wave function that you don't know. So one method to deal with this is self-consistent field. So you first guess your initial wave function, and that is parameterized using a set of basis functions. And really, how you parameterize a wave function determines the accuracy and the complexity of your method. Then you calculate the Hamiltonian in a matrix representation. So basically, the representation of the wave function also determines the representation of the Hamiltonian. And then, since this is a density that's over space, these are not just a couple of sums. You actually have to solve some integrals here. So this is kind of heavy. Then you can diagonalize your Hamiltonian. You get a new wave function, and then you start again until this converges. This is really, really short. But basically, what you need to actually get to your wave function is the Hamiltonian in the step before the convergence. So what is called the ground state Hamiltonian. And this is exactly the property we aim to predict here. So the architecture that we developed is called SNORP, Net4 Orbitals. And so this might look familiar. So this is actually the embedding again. And then we have a couple of Schnet layers and we get our representations per atom. But now we also, since we want to predict a matrix, so the Hamiltonian is now in matrix representation, we need to predict pairs of atoms, and it's also not rotationally invariant anymore, but the rotational symmetry depends on the basis function we choose. And we did this fairly agnostic here. We just said, okay, we have this SNORP layer. We take two representations of a pair of atoms through this tensor layer, which is, let's say, a generalized form of the continuous filter convolution. And then we get pairwise features here. And these are still rotationally invariant, but we use this equation 5 here by projecting it to the directions of the distance. So how do we say it? The directional cosines, basically, on the normed distance vectors. And the final features are cumulative products of these features, because if you have only one, then it has basically rotational. Your angular momentum is 1. So basically, you rotate once, and it's one full sine. And then if you have higher polynomials, you get more and more angular momentum orders that are allowed here. And then you can use these features to predict the entries of this Hamiltonian. So I hope this was not too confusing. But if you want to know details, you can ask questions later about this, or read the paper. I guess that then it gets more clear. Then I can do this in this short time now. And then if you have the Hamiltonian, you can diagonalize it. You get the wave function, and here are some things you can do with it. For example, here on the left side, we show a proton transfer. So you have the malon dialdehyde, and there's this hydrogen here connected to the right oxygen, and then during the molecular dynamics simulation, it moves over here to the other oxygen. So this bond gets dissolved, and this bond forms, and we predict here the molecular orbitals that are involved in this prediction, and also we can obtain directly from our prediction the electron density during this transition. And another thing we did with that is since we can predict a wave function, we can use this as an initial guess instead of the heuristic guess that you normally get, and directly put this prediction into a quantum chemistry code as a starting point for a calculation. And here you see if we do that. So first of all, we saw, okay, we don't get much less iterations of our self-consistent field procedure. But that was basically because these optimizers are really, designed so to work very well with the usual quantum chemistry guesses. So we used the Newton optimizer instead, which is sadly a bit more costly. But you see, then you get you use much less iterations, while if you would use a Newton optimizer directly on the quantum chemistry initial guess, it would not converge. So, and here are some other derived properties you can get. You can get bond orders and partial charges. So bond orders, like here you see 2, so this is a double bond and this is a single bond and so on. And we also used it to predict the Hamiltonian in a minimal basis Hamiltonian. So normally you have a larger basis set than you have electrons, and there are some methods to then reduce your Hamiltonian to a minimal basis, so you only have the number of basis function is half the number of electrons, because you have 2 electrons per state. So and here we predicted directly this kind of reduced Hamiltonian. And since we now have direct prediction, direct access to the electronic structure, we can also directly optimize it in a gradient-based way. So here in this case, we started with a band gap of malondialdehyde and then minimize it and maximize it, and then we see here how this affects the orbitals. In this case, so the highest occupied and lowest unoccupied molecular orbital. And this is just a local optimization, but you can also think of making this part of a global optimization, for example, with alchemical derivatives, where you can actually change the atom types and remove atoms smoothly. So there's a topic I don't want to go into too much in this talk. But basically, this is just a first example of what you can do with this kind of access to the electronic structure. So how I'm on time, half an hour, okay. So a different way to unify machine learning and quantum chemistry is through the surrounding workflows. So the quantum mechanics code is the one thing, but then you have the simulation around it. And one way to do this is through external fields, because you often don't want to simulate a single molecule in vacuum. You actually want to simulate it in solution. So for example, not just one single ethanol, but a box full of ethanol. Or you also want to get the spectrum of this molecule so that you can compare it to experiment, because in experiment you don't have measures of the positions of each atom. You have a spectrum that you measure, that you can then try to relate to the structure of the molecule. So in here, in this field Schnitt approach, we did just that. So on the left side here, this is basically the basic Schnitt architecture. Here, these continuous filter convolutions, here we call charge-charge interactions, because we have actually a scalar. So it's like a charge on each atom that only depends on the distance to the next atom. And on the right side, you have the extension to dipole features. So it's vector features. So this is basically an equivariant network, if you heard about that. So on each atom, we now also have a local dipole. So a vector like here. So here, before we just had points, now we have vectors. And this is polarized by the surrounding atoms. So the direction depends on the surrounding atom. So if you rotate the molecule, these vectors rotate with it. And then we have additional interaction terms that you see on the right side here that are basically inspired by electrostatic dipoles, and then use neural networks to model the the radial part. So basically, the rotation is given by the symmetry, and the radial part is is modeled by a neural network. And you see here, this is what SNET would look like. So this looks, yeah. So this is like the features for the whole molecule. But if you look at a single atom, of course, it would be radial because we use radial filters. But if you now have these dipole features, you see that even for a single atom, you get a dipole and you get a more complex structure. And on the right side here, you see now we have an additional input, which is the external field. So like an electric field that acts on the atom that that gets picked up by this dipole field interaction. And now you see here you have the symmetry of the molecule is reflected by the symmetry of the representation. But now if you add this field, this external field, you see that the symmetry of the representation gets distorted by the field. So, and now what you can do with it now is that a lot of spectroscopic properties like the dipole moment or the polarizability or the chemical shifts are response properties of the energy with respect to an external field. So you can really simulate your the molecular dynamics, and during your simulation you can calculate the response properties. So if for the dipole moment that corresponds to the infrared spectrum, the polarizability to the Raman spectrum, and then these chemical shifts you can you use in NMR spectroscopy. So this is really then a nice way to connect your simulations to experiment. And also what you can do is if you have your molecule in solution, you can say, okay, I will do the quantum calculation only for this molecule, and the rest of the molecules are modeled by either some kind of implicit continuum model, or by a molecular mechanics force field, which is even faster than machine learning. So you can use the external field as an interface between your machine learning model and a solvent model on the outside. So here we have two kind of solvent models: the ML with the polarizable continuum model, and machine learning with a molecular mechanics as a solvent. And you see here for the MLMM that here the red curve in this lower frequency area aligns much better with the experiment in gray. So this ethanols in ethanol solution. And we applied this also to a Claisen rearrangement reaction. So we have this molecule here, and then you see this one bond here goes away, and we have a bond forming here. And during this reaction, you have this kind of reaction barrier. Whoops, sorry. This kind of reaction barrier. And you see, if you look at the red line, which is this the molecule in solution. So this is in water. Then you see a much lower reaction barrier than you would have with a molecule in vacuum. And here on the right side, you see why this is, because when this bond dissolves, there are some non-bonded interaction of the oxygen with the hydrogen of the water solution. And again, we attempted some inverse design here, and we said, okay, can we get a molecular environment as a solution that lowers the reaction barrier? And so the way this was done is by just using gradient descent to optimize the external field that would lower the reaction barrier. So here you see the charges. I don't know, one of them is positive, one is negative. I always forget which is which. But this is basically the optimal charge environment for this reaction. And this would reduce the reaction barrier from the initial, almost 35 kcal per mole to 10 kcal per mole. Now, obviously, you can't really get any kind of charge environment. This is an example how you could get something approximately like that. So you could have these leucine and asparagine amino acids surrounding the molecule like this, and which would give similar local charge environments here. And that would still lower the reaction barrier to 20 to 25 kcal here, which is much lower than the original one. So this is another, so this is now another example of inverse design where you first relax the space in which you optimize, and then when you have your solution, you go back to the concrete thing. So as a last topic, really quick, you've seen some generative models for graphs already. We did something for 3D structures. So basically we have a autoregressive model that we first place one atom, then we want to place the next one, and we still want to retain the symmetries of the molecule. But since we do this with radial filters again, our local symmetry is actually higher than the actual symmetry of our target molecule. So what we need is some focus token which breaks the symmetry so that we don't get these artifacts here in the middle, and then we can build up a molecule. And this is again based on the Schnedt architecture, where we have first the Schnedt interaction layers, then we predict the next atom type to set, and then in the end we predict some kind of distance distribution and draw from it to place the next atom. So we start with the center token here to keep the molecule compact, put the focus token there, then place the first atom, put the focus token there, and then place atoms one after the other. And at some point, the model predicts stop as an atom type, and then the focus token doesn't go back to the finished atom. And this is how we build up atoms. And I think I'm already really late, so I will just show you this as a last point. So we also trained this on a QM9 data set, but we also trained this only for molecules that had some desired properties. So large homo-LUMO gap here, for example. No, this is a low homo-LUMO gap, for example, and then you see how the distribution of the target changes, and we actually could generate some novel molecules that were not contained in the data set before. Yeah, so my conclusions, there are very different ways to unify machine learning and quantum chemistry, and you see this in a lot of communities in DFTB, as a tight binding community, where they start to build machine learning into their methods, and you see that in the workflows, in dynamics, in inverse design, keyword closing the loop. So I'm really excited to see this happening, and I'm really interested how this what will happen in the future, because there's a lot of moving. And so thank you. And one last thing, so Michael Gastegger was the first author on FieldNet. Niklas Gebau was the first author on the GSNet, the generative model, and a lot of the ideas for the SNORP for SNET for orbital SNORP came from Reinhard Maurer from University of Warwick. Thank you.
Thank you, Christoph, for that nice talk, and yeah, the incredible amount of work you have done in this space. Yeah. So there are one question which is a little bit detailed, but and that can we use your codes or similar machine learning based method for atomic systems, like calculating MBPT based properties with lesser computational cost, for example?
Okay. Well, what was
for atomic systems? So I think the question is beyond your applications, in which other fields this codes can be used. So that is I think
which
more general.
do you mean beyond atomic systems?
Yeah.
Okay.
No, yeah. Sure.
Right. I mean, so I mean, basically the main point of the data is that it's points in space with a type, and so basically, if you have some kind of graph that is embedded in some kind of Euclidean space, then this is applicable, right? So, and there's also a lot of theoretical work that goes further into what kind of equivariance properties you can incorporate into these models, for example, by Risi-Kondor and by Tess-Smith. And I think this is really similar from the mathematical point of view. And so it's a lot of the, I guess, also manifolds could be an application area.
Yeah, so I think the question was a little bit, so you have used it for molecular systems. So people are asking that whether it can be used for atomic systems. So that was
Atomic systems.
Yeah, that was.
I mean
So
molecules are
yeah
somehow atomic systems, right?
Yeah.
So I'm allowing you to talk. Please say.
Oh, thank you, sir. Thank you. Actually, my question was, can we use, these kinds of methods to calculate the many-body perturbation theory type of properties for atomic systems? Like machine learning, can we use it to reduce the computational complexity for calculating MBPT type of properties, like, second order, third order Stark shift in atoms, which is very computationally intensive. So can we use machine learning there? That's my question, actually. Thank you.
Okay, I'm not that familiar with this part. I would have to look into this. I'm not sure what the actual data there
that is fine. Yeah, that is fine. I think there are a lot of things which are there. So one very general question is, you are talking with physicists, chemists in doing this type of works. So how is the reaction? Are they happy with your results, or not so happy, more things to be done? It's just you're scratching on the surface. Yes, I'm just asking an honest feedback from chemists.
I think currently, I guess it depends a bit on which community you're talking about. But at the moment, there are, so in quantum chemistry, a lot of people are really excited about machine learning. And I mean, also, this is not really machine learners taking their methods and going to quantum chemistry guys and saying this is how it's done. They are doing, they apply more and more machine learning themselves, and especially in method development, in DFT type binding. You see a lot of work. So I think it's really, I think people are really excited about this. I mean, there's still a lot of work to be done. I mean, most of the things I showed today is really small systems, but yeah, we get solution now. We go into reactions. Yeah, I think it's a very what do you say? So a lot of work is currently happening in the field, and
so I will
feel the excitement.
Yeah, sure. I think this is a good answer. So I will just ask any of the panelists if they have a question, they can go. Yeah.
Hi, Christoph. This is Animesh here. So this is a general question to all the speakers in this session. So I was just wondering, like, if like models have been built uh, like with this explainability embedded in it, like whether the models that are being built in this area, like, are they explainable? So this is a question to you as well as Brooks, like, are there works that you know which try to be like, you know, apart from doing predictions or some sort of ranking, they also try to give an explanation to why the model is behaving in a particular way?
Yeah, so I think the problem with explanations is always to first define what an explanation is, right? So I think the more basic your predictions are, the more explainable they are. So if I predict the energy of a molecule, right, it's as a sum over atoms. So I what I see from the model is where it locates contributions to the energy in the molecule as a basically as a latent variable in the model, or as a neuron in the model. So I can directly relate to this because there's no nonlinearity between the atomic contributions and the final energy. So a lot of explanation is actually location. So if I want to explain why is this image a cat, and it shows me, oh, there's a cat, that this is a part of the image where I see it's a cat and there is a cat, then you can see that as an explanation and not of some, I don't know, watermark that's in the corner of every cat image, right? So that would be a wrong explanation. So I think it gets more complicated the more abstract you get. So if you want to predict very complex properties, I don't know, is this toxic, right? then it gets more complicated because then you are there are some abstraction levels in between. But the energy, it's just, if I stretch the bond, the energy goes up, right? It's just about the quantity that's where the neural network is really used in this case.
Okay, thanks a lot.
So thank you, Christoph, for this nice and wonderful talk and the amount of work you are doing.
Thank you for the invitation.
Yeah, thank you. So the next talk and the last talk in this now evening is Abir Day, and he'll be talking on Nibhai, deep generative model for molecular graphs. So just to give an introduction, Abir is an assistant professor in the Department of Computer Science in IIT Bombay. Before that, he was a postdoctoral researcher in Max Planck Institute of Software Systems at Kaiserslautern, Germany. He was where he was hosted by Manuel Gomez Rodriguez. He received his PhD from Department of Computer Science, IIT Kharagpur. And during that time, he was part of the Complex Networks Research Group, and he was also supported by Google PhD Fund, a PhD fellowship. He got the INE based PhD award, and he also did his BTech and Masters both from IIT Kharagpur. So Over to you, Abid.
Okay, thank you. So now the screen visible?
Yeah.
And am I audible, right? Okay. So it's in full presentation mode, I hope.
Yeah.
Okay, thanks. So thanks the organizers for inviting me for this talk. So this talk is on Nevi. It's one of the, I mean, it's one of the old generative, deep generative model for molecular graphs. So nowadays there are more molecular generative models, but this is kind of one of the oldest of its kinds. And this work was done with collaboration with Bidisha Samanto, Gaur Harijana, Pratim Chattaraj, Professor Niloy Ganguly, and Manuel Gomez Rodriguez. And though I am currently affiliated with IIT Bombay, but I did this work when I was a postdoctoral researcher in Max Planck Institute. Okay. To start with, I think it has already been motivated by all the speakers here. So discovering new plausible drug-like molecules is a challenging task, and it involves, 3-4 steps. So at the very first step, you first find a set of candidate molecules, and then you go for preclinical development where you filter out some molecules which has low rate of therapeutic discovery, and then you go for clinical development, and which has a lot of sub steps, and finally you get a regulatory approval. And this all involve well-class testing, and that's why it's very complicated task in terms of scaling, cost, and everything. So what if we sort of give like automated machine learning based molecule design? Even if it doesn't give very accurate result, it can give some cues, some candidate molecules to the chemist, so that after having these candidate molecules, they can take over from there. And driven by this motivation, there is a flurry of works on deep generative models on automatic molecule design, and mainly follows two types of approaches. So the first approach is text-based approach. So they basically represent molecules using some custom string called smile string, and then they use off-the-shelf deep generative models for text, and they apply on the smile strings to have like deep generative text models to generate new strings, and then they convert them to the molecules. The second approach is graph-based approach. So they don't convert them into text, rather they take the molecule in the graphical form, and they apply or develop novel deep generative models specifically designed for molecular graphs. Okay. So there is a certain limitation from text-based models. So at the first, smile strings, that is the custom strings that heavily rely on this, that heavily regulate these generative processes, they do not capture structural similarities between molecules. So you convert a molecules into some text. By looking at the text or by comparing to text, you cannot tell about the structural similarity between two molecules. Secondly, a single molecule can have multiple smiles representation. And these two things result in lack of diversity as well as validity on the generated molecules, because validity mainly arises from the graphical structure of the molecules, and the text cannot capture that. So therefore, if you generate new text based on the existing smile strings, it may not ultimately result in a valid molecular graphs. And moreover, because of the structural similarity, there the texts are less granular, which result in a lack of diverse molecules. Okay, and to overcome these limitations, graph-based approaches have come up, and it turns out to be that the graph-based approaches are more effective in generating valid and diverse molecules. However, they only generate molecules which same number of atoms. Moreover, they are often not invariant of the permutation of node levels. So what I am saying here is more or less that more like this. So you generate a molecule. If you change the labels of the nodes, or you shuffle the labels of the nodes, then the molecule that you get, or the distribution from which you are sampling the molecules, they change. As well as similarly, after that, you also, the training parameters that you essentially train over the existing training set, that also can change if the model is ultimately not permutation invariant. And finally, some of the models, some of the approaches, they generate molecular graphs by combining a small set of graphlets. Okay? And these three result in a lack of diversity on the generated molecules, especially by the second and third points, because you have a set of vocabulary and then you sample molecules from based on this existing, graphlets, and then you plug these small graphlets or small molecular parts to get a big or complete molecules. And since you are sampling from an already existing vocabulary, so ultimately you get a limited number of structures, or you get a limited set of structures, molecular structures, which result in a lack of diversity of the generated molecules. So we overcome these limitations in this work by providing a new model called NEFI, which is a network variational autoencoder. So like other variational autoencoders, there's two parts. So the first is a probabilistic decoder, and the second one is a probabilistic encoder. So by probabilistic encoder, we just translate the features. We just translate the features, the age, everything in a latent space, and we convert them in the finally in a more probabilistic decoder. We finally help in generating new molecules. Okay. So this involves several key innovations. So in encoder, we use aggregator functions from representation learning, and they finally learned using variation and inference, and it finally gives permutation invariant variable size graphs. So this is mainly because the aggregator functions, which are mainly driven by graph neural networks, they are permutation invariant given by the Desideratum by deep sets. In the decoder, we use kind of structural and functional masking functions which guarantee the properties which are specific to the molecules. So we'll see that how we can ensure the valency properties or other chemical properties using this masking function, and these kind of masking function finally results in a high validity. And finally, we see that the inference, we use kind of a single multinomial age distribution, and it results in high scalability. So we'll now discuss each of these three things in the subsequent slides. So first we come with the probabilistic encoder. So what we do here, we first compute the node embeddings using symmetric aggregator functions. So for each node, we compute the embedding by collecting information from its neighbor. Then we pass them in the neural network and at different hops. So for example, if you see that for node V, we convert them using graph neural network, a set of embedding, and then for this embedding, which is say for example a jth hop, we pass them in a complete feedforward neural network, and we get a set of node embeddings for different hops. Okay, and we cast them in a latent variable distribution using these load embeddings, and the hope is that the latent space will map the structural properties. So the idea is that if you see this, these two substructures are kind of structurally similar, so the latent in the latent space, their properties of the distribution will be kind of similar than what is far away, than the structure which is far away from this small graphlets. Okay. And this encoder has desirable properties. So first of all, for each node U, the embedding CU is kind of invariant to the permutations of the node levels and its neighbors. So see this particular situation where we can have like a node U and it has several neighbors like U6, U5, and I get a node embedding says CU, and suddenly if I change the neighbors, the labels of the neighbors for not only for node U but also for other nodes, I get the same node embedding CU. Okay, if I just shuffle the label, then I get then I have like permutation equivariance. So the idea here is that if we permute the node labels, the embeddings get permuted in the same manner. So suppose I have a node labels order like U, V, and W, and if I just change the labels like U, V, and W in a different manner, the node labels also, the embeddings also change in the same manner. Okay, and it is important to note that the weight matrices or the parameters, they do not depend on the number of nodes or edges. So by saying so, we ensure that our model both encoder and decoder will be able to capture different size graphs. So more specifically, the decoder is being able to generate graphs which have different sizes, and the encoder will be able to embed the space, the training space, or the molecular space in latent vectors, which have which can capture like different dimensions. So basically, we also model the number of nodes and number of edges as a part of our model. So that will something that we'll see. So the probabilistic decoder has kind of several parts. So at the first state, we convert a given molecule, if it is given, into random vectors, that is latent vectors, that is Z. The idea is that we believe that this is a graphical space, non-Euclidean space, and we can approximate this Euclidean structure into a non-Euclidean structure into some Euclidean structure. Okay, and suppose I ask you to generate a molecule from scratch. So you are not given a molecule, and I just ask you to generate a molecule from scratch. So what we'll do? So first, what I will do is I will sample the number of nodes. So we generate the most common distribution from which you can generate the number of nodes is the Poisson distribution. And then once I generate the number of nodes, I will simply convert them into, I mean, for each node, I will generate a noise because I don't have any graph. I just want to generate a graph from scratch. And I will get this noise as a representation of the random vectors. So now the random vectors, in case of, in absence of graphs, they are simply noise. Okay. Then once I generate the node representations, then I will sample the node features, okay? Because I have generated some nodes. I don't know what is this features. This features indicates the node levels. So for example, it can be carbon, oxygens. So in our work, we assume the features are sort of this one-hot embeddings, one-hot encodings of these node levels, okay? So we sample these node features or this one-hot encoding or the node types, whatever you say, from a logit or softmax distribution. Okay, and now the generated graphs looks like this. You can assume that different nodes, these colors indicate different kinds of atoms. Okay. However, there is still a lot of things to go because you have to connect edges and you have to connect the number of bonds, etc. So what we do here is the following. So we sample the number of edges from a Poisson distribution again, because it's the integer, and we sample from a Poisson distribution, which depends on the set of latent vectors that you already sampled. So basically it depends on the Z. Okay. And then we sample it we sample the presence or absence of an edge UV based on some softmax distribution, and which is characterized using the which is the pairwise some pairwise function between U and V. And once I generate this these edges, that is whether an edge is present or not, then we sample the number of bonds, which is basically we treat them as an edge weight. Okay, so that is something that we also sample from the softmax distribution. Okay, so finally we get the graph like this. So first we sample these edges, and then these edge weights. Okay, so the decoder finally guarantees the structural properties. So how do we do that? So you see that we have generated, say, for example, k-1 edges, and then we want to generate the new edge. But suppose that this new edge turns out to be a carbon-oxygen bond or a carbon-carbon bond which violate one or two valency rules. So at each step, we basically check that. And then if we find that there is some violation, we essentially disable that potential edge, and otherwise it will violate the valence. So then we sample the kth edge from the multinomial distribution. So if you see that this particular edge will be violating the valency, then we basically make these probabilities from which we are going to sample to be 0, and then we effectively sample from the rest of the slots. And this is the only chemical rule that we are incorporating using mask, the reason is as follows. So there are a lot of chemical rules. So why don't we characterize everything by form of mask? The main reason is the following, is that these rules are easier to check. But if you like check for bridges and everything, for each step of generation, you need to traverse the entire graph, which is computationally very costly. Okay. So now we say that this is finally a VAE, and they are typically trained by maximizing elbow using stochastic gradient descent. But again, as I said, we sequentially generate edge, and then how to ensure that a permutation invariant ordering of the edges on the training algorithm. So basically, we then sample all sorts of sequence of edges, because in the training set you are not given the sequence of edges. So to ensure that this still fits in the sequence driven generation, we first sample a sequence of edges based on this BFS and a source node sampling, and then take Monte Carlo sampling. So you can think that the overall procedure treats all permutation to be equally probable. So basically saying permutation invariant may be slightly misleading, because it's after all depends on the number of Monte Carlo samples and the distribution. But finally, you can think that, okay, as long as the permutations are equivalent, then it's like it finally gives a permutation invariant node weights. Okay. And the training is efficient because this H partition function, it's actually which can cause a bottleneck that can be overcome by a negative sampling from NLP literature, and then we go down from V squared to E, the order. And finally, in experiments, we sampled 10,000 molecules from 2 datasets to drug-like molecules, to datasets consisting of drug-like molecules. So one is zinc, another is QM9. And for each molecule in each dataset, we construct a molecular graph, and nodes are atoms. Node features are simply one-hot encoding of its atom type, and then edges are bonds, and edge weights are like single, double, or triple bonds. For each dataset, we train 2 different models. One with masking and another with without masking. And qualitatively, we find that if we sample from these, if you try to generate conditioning on this particular molecule, we get that qualitatively similar molecules we are being able to generate. So quantitative evaluations are as follows. So we consider 3 metrics. First is validity. So it is basically percentage of chemically valid molecules. So here we can see that one of the molecules are basically breaking the valency rule. So the validity is 75%. And then novelty, so percentage of chemically valid molecules which are not present in the training set. So if one valid molecules is found in the training set, we discard that. And the uniqueness is the amount it measures the diversity. So in other words, if 2 molecules or 3 molecules or one molecule is generated multiple times, so there is a penalty. So here you can see the uniqueness is kind of 50% because the first 2 molecules are same. Okay. So there are 4 graph-based computing methods and 3 text-based computing methods that we take. Okay, and Nevi is star is our model without masking, and we see that graph-based methods are performing very well, and also there are several methods that are giving good fights, as you can see, like junction tree variation or autoencoder. Text-based models are kind of underwhelming. The novelty of the discovered molecule, you see that the most of the models are fine. It's basically because it's basically conditioned on the number of valid molecules. And since even for the text-based molecules, you see that number of valid molecules are very small, we see that novel molecules are very high. But these novelty metrics are alone in incomplete. You have to also consider the valid molecules, because these 100% molecules that are novel may be like they are very small in numbers, because most of the molecules may be invalid. And this is the uniqueness of the discovered molecule. Again, we can see that with masking, we are being able to generate unique molecules. So as we can see, that different algorithms are performing very well in terms of different metrics, but our model is being able to perform reasonably well across all metrics. So that is one good point. So in conclusion, we have introduced a variational autoencoder for molecular graphs, and there are a lot of technical innovations, and now these works are being used as a basis for different molecular generative models now. And there are many interesting questions. So first of all, whether we can do chemical synthesis, simulate chemical synthesis, then we can do retrosynthesis. For example, we try to find different chemical compounds given the final product. And there are a lot of other applications of generative models for graphs, not only molecules. So for example, you want to generate a new image based on scene graphs. You want to do generative search. Those problems are very interesting. So that is all. And over to questions.
Thank you, Abir, for this nice talk. So, I would open it to the panel for some questions. Yeah.
So Abid, this is Animesh here.
Yes, hello.
Can you hear me?
Yes, hello.
Yeah, hello. So I was just wondering, like, whether these kind of models can be also used for, little high level kind of applications like drug repurposing and things like that. I mean, when you talk about retrosynthesis and this applications like those, that immediately struck me to, like, even higher applications like drug repurposing and things like that. I mean, just what are your thoughts on it?
That's a good point. Actually, so there is a follow-up of this work because of the time constraint I did not include. So that basically try to generate molecules with desired properties. So you basically specify a property and you will get a molecule that satisfies this property. I think drug or retrosynthesis or drug repurposing is kind of arise from the same thing. So retrosynthesis is kind of inverse, reinforcement learning kind of thing, right? Because you know the reward and you try to trace back from which state you should go to reach that reward. So you are given a final product and you want to trace back. And basically this existing techniques basically follow this reinforcement learning combined with Monte Carlo tree search. And yes, this kind of work follow this, but not like, this model immediately will give you that kind of problems or solution to that problems. So after this generative model, you can use at a, footstep, and you have to apply like reinforcement learning, Monte Carlo tree search, all this thing to get to this drug repurposing or retrosynthesis. So the forward problem is very easy, and this gives a this kind of models gives you a strong basis or strong tool to tackle the front problem, be it like goal-oriented design or chemical synthesis, because you need to traverse the graph where the electron is going to attack. I think Miguel, who is a speaker here, has a paper on that. So there the idea is that you traverse the graph and then you find the weak spot. Okay, break the molecule there, bring another molecule and connect it so that they get a final meaningful compound. And if you have like lot of chemical reactions in your data sets, you can train your model based on that. But the opposite side is kind of difficult, although this you have to use this, but there needs a lot of techniques.
Sure. So Bhavesh?
Yes.
Yeah, I have allowed you to speak. So can you?
Okay.
Yeah.
Yeah. Thank you.
So I can see the questions. Should I take it?
But he's asking the question anyway. Yeah.
Oh, because he has already written, so that's what I'm asking.
Yeah. Thank you, Abir, for the talk. I have two questions actually. First is when you say novelty and other features while you are generating these molecules, you sort of use them to, use them in the loss function so that you enforce more novelty,
That's a good question. So can I take one by one? So the first question.
Yes, please.
Because I can see the question, so it will be good. Okay, so that's a very good question. So your question is that we are just treating everything in an unsupervised manner. There is no component which are directly associated with the matrix we finally use to evaluate in the loss function, right?
Yeah, I'm just like, how do you enforce that you generate more and more novel molecules?
That's something that we don't do. That's something that we don't do.
Okay.
I think novelty, to say in this way. So novelty is something that, you want to generate a new molecule which is not present in the training set. In my understanding, if you do it randomly, it will be more novel.
Yeah.
So I don't think that novelty is something that you really want to enforce in the loss function, because it's finally you want to, you embed the graph in a continuous distribution, right? And you sample from continuous distribution. It's very unlikely that you get two random variables which are near or, which are same, which are sampled from the continuous distribution. And finally, that gives you a high novelty, right? So I think that comes from the fact that any model which is like continuous, which are sampled on a continuous space, that they are likely to give very high novelty. And it is true that we actually run like 10,000 or like 1 million sample, 1 million run to repeat a molecule. This is something that because there is the space is quite spreaded, and that's why you sample, it's very difficult to get the same molecule, because there are a lot of randomness, not only the original random latent variable, but also the sequential generation, that is also kind of random, right? So there is a lot of source of randomness, and to get the same realization once again is very difficult. So ideally, what will be nice to check is that, if two molecules are close, then we collect them, they're not novel. Like, a model is very close to the training set structurally or property wise, or in some sense, then they are not novel. Then I think it will be a more interesting metric, but I don't know what is that application. But technically, that is more, that can give more insights into this fact.
Right.
Okay. And the second question
is. So Surya has some questions. So
I had a second question.
Oh, I
had a second question.
Yeah, yes.
Surya, please wait. Okay, we'll allow you to speak.
So, Abir, my second question was, you said conditional generation of molecules. Are you saying that you can, for a property, you can say, oh, this is the property I'm looking for, so I'm generating this molecule. Is that correct?
So this is something that we have done. So we have an extended JMLR paper of this IEEE paper, which deals with that you want to generate a molecule that has low toxicity or high solubility, okay, or high magnetic dipole moment, or whatever property that you want to whatever property that you want to
okay.
But here the point that I'm saying is conditional generation of molecules is the following: that you are given a molecule and you want to generate a molecule which is semantically same. By semantically same, I mean, okay, the structure, the properties will be kind of same. I don't know how. So what we do here is this following: that we take the molecule, we embed into the latent space, okay, using the encoder, because the encoder is basically the distribution Z conditioned on the graph, right? And there we get the latent variable. And from the latent variable, by conditioning on the graph that you are given, you now generate a new graph. And then the final generated graph is kind of semantically close to the original graph that you started with.
Right. That because we are sampling from the same space as the training molecules. Yeah. Okay. But I am interested in your follow-up paper also. So maybe I'll take it offline. Maybe I'll send an email to you.
I think if you search by the title, you will get the archive version, and that contains the details.
Great.
I'm also happy to chat whenever you want.
Yeah. Thank you so much.
Surya,
hello.
You have
yes, sir. I've got a question.
Yeah.
Actually, good evening, sir. I wanted to know what are the free and open source softwares to check the validity, novelty, and uniqueness.
Okay.
In a particular kind of research.
So think of novelty and uniqueness. I think you can just right. You can just check for each of the molecules that you have generated whether they are present in the training set or not. That is very simple. So, but I know what is your question now. That checking for each and two graphs are difficult. So this question. So basically, there is a tool called RDKit, which translates a molecule into smile strings that I actually told in the first few slides, right? There is this tool called RDKit. So these RDKit is the chemoinformatics tools which can provide lot of chemical signals, like for example properties, whether their molecule is chemically valid. So they just check for some like 20-40 rules, and if all the rules are satisfied, then they say chemically valid. except for one rule, we don't incorporate anything explicitly in our model. Only one rule we take into account, which is valency rule, and rest of the rules we learn passively. And we see that, just by incorporating one rule and from the data, like this 10,000 samples that we learn, we get quite a bit high validity. But this is something called RDKit. I think that is something that you are asking for.
So I think there's a last question which you can take. Are these generated compounds validated by chemists?
Okay, so the results that we report is like over 10,000 molecules, or like 1,000 molecules that we generated, and then we compute uniqueness, validity, and novelty, and that is difficult for this 100 compound to be validated by chemist. As I say, there is a tool called RDKit which directly can tell whether a molecule is valid or not. So you just give the molecule input and it says 1 or 0. However, in our team we have chemists who actually, qualitatively they have seen the molecules and they said that, well, these molecules, I mean, many of the molecules make sense. Not of course everything, but most of the molecules make sense, and that's why I think that that tool has some value.
So any further question anybody has? Or I think we can call it a day. So I think I should thank all the speakers in this session. It was very nice, and we got a lot of perspective. We got a lot of perspective in this emerging field. And I hope the speakers have also got a lot of, the attendees have also been benefited from this type of diverse talks. So thank you, and we close the session now, and tomorrow we reconvene at 8:30. Anirban, so
8:15. 8:15.
8:15. We reconvene at 8:15. Yeah. So 8:15 we have the next session. Okay. Then good evening.
Bye.
Bye.